All right, thank you so much for giving me opportunity to share our thoughts about last mile delivery of hydrogen. I say hydrogen because end of the day, when we talk about the last mile delivery, when the hydrogen is produced, it becomes agnostic of the color. So we will talk about certain challenges about green hydrogen, but once the locate, if it's a distributed production of a green hydrogen, then it's more of a last mile delivery of hydrogen and what we need to consider. Okay, next slide, please. All right, so I will quickly run through if for the interest of the audience the who Linde is and what we are and why we believe that our message is important for you to understand about infrastructure development for the last mile delivery of hydrogen, and then how the cost of hydrogen breaks up when it comes from the generation point to the delivery point, depend upon the delivery, how the distribution and infrastructure cost impacts on overall hydrogen cost, and what are the different hydrogen distribution pathways for last mile delivery of hydrogen, and how it compared one versus others, and what needs to be looked at when we select the one mode versus the other mode of hydrogen delivery. Okay, next slide, please. All right, so quickly about Linde. So Linde is now world's largest industrial gas company with a $160 billion market capitalization, and after merger with Linde and Praxair, we are spread across the globe, supporting the all industrial gases business. And particularly we have our own technology as well as our own uh, execution arm and operating capabilities, and we invest into quite a bit of the projects to develop our industrial gas application, which includes the hydrogen. Okay, next slide, please. Okay, so the key point here is how we fit into the hydrogen value chain. And if you see here, on the left hand side, it's a hydrogen value chain where hydrogen is first produced, then hydrogen distribution, hydrogen conditioning, and then it's an end application. So if you review, Linde goes to the partner for either getting the natural gas or renewable power, and then be it a gray hydrogen, blue hydrogen, green hydrogen, or brown hydrogen, Linde has its own technology to produce hydrogen from SMR, carbon capture, CO2 recovery, as well as electrolysis to produce gray, blue, green hydrogen. Once a hydrogen is produced, it requires its distribution, which is the key topic here, and that also needs to be very clearly been looked at because it's a very critical point from the production to the delivery point. So distribution of hydrogen happens with the different mode. Linde has its own liquefaction technology which can liquefy the hydrogen for liquid hydrogen supply. We are also supplying hydrogen in trailers in the gaseous form as well as liquid form. We are currently operating 1000 plus kilometers of pipeline in US, which is another mode of the distribution of hydrogen, as well as for the continuous supply of hydrogen. We are the one with operating the world's largest salt cavern in Texas, where we are storing the hydrogen underground and managing the hydrogen highway with for the reliable supply of hydrogen to the key applicants like refinery and fertilizers. The next is hydrogen conditioning. Hydrogen conditioning is also important based on the end application. If it's hydrogen mobility, then the hydrogen refueling stations required a conditioning compression system based on we are refueling cars or trucks. as well as if it's going to the refinery or fertilizer, they have its reliability as well as the purity specifications, and that needs to be looked at. And Linde has its refueling stations technology also for mobility, as well as the ammonia and methanol technology for making the end hydrogen products. So if you see, we have a leadership role in technology as well as operation, from supply chain, starting from the production of hydrogen to the consumption of hydrogen, that also blue and green hydrogen, as well as providing the distribution and the conditioning of end application. Next slide, please. Okay, so as I mentioned that production, then processing, then distribution and storage, and then the end application, and then the end use. These are the 5 steps of hydrogen production to the hydrogen end use. And if you look at the graph below, you will be amazed to see that when the hydrogen is produced, from the $1 to the $3, depend upon the color of the hydrogen, to the point that hydrogen reaches to the end application, the cost of hydrogen increases by 2 to 3 times. What that means is that the hydrogen cost is not only dependent on the production route, but it also very much dependent on what's the last mile delivery methodology being used and what's the end application, because that optimization also plays very important role when we decide the hydrogen cost. So lot of forums, lot of discussions, you hear that somebody able to produce the hydrogen at $1, $4, $5. What's really important is what is the delivered hydrogen cost, and for that to reach a very optimum level, what should be the right pathway and what should be the right medium of hydrogen with that achieves the optimized cost. Because there are 3 or 4 pathways. If you see, if you decide to transport the hydrogen in a gaseous mode, then you will have to compress it after the production. So this is the place, the first bar chart after production is compression or liquefaction. So if you decide to transport the hydrogen through the gaseous hydrogen, then we need to compress it. That requires additional power, and but then compressed hydrogen can be put into the tanker, and then it goes to the hydrogen refueling stations, where it gets further compressed for the pressure required for the bus, trucks, or the cars. If we decide to transport that hydrogen in liquid form, then it requires a lot of energy to liquefy that hydrogen. But then the cost of distribution goes down drastically, because the liquefied hydrogen takes almost like 1/7 of or 1/10 of number of trucks required or tankers required, which is the cryogenic tankers, to distribute that hydrogen. So either the high cost of liquefaction and low cost of distribution versus some cost of compression and additional cost of the distribution decides the overall optimum infrastructure cost for delivering the hydrogen from production point to the end application point. Okay, next slide, please. So this is to give you some kind of the perspective that the left hand side is the liquid hydrogen tanker, which can carry up to the 3.3 tons of hydrogen, versus these are the different pressure hydrogen gaseous based tube trailers, which can carry half a ton to 0.3 tons of the hydrogen into the tankers. What that means is that the liquid hydrogen tanker can carry almost like 7 to 10 times of the hydrogen in one ferry or one round trip. That means is that the overall cost of the hydrogen delivery through the tanker goes drastically down, and the investment in the tankers and the cryogenic VRV goes down for the liquid hydrogen based. However, what it adds is the cost of the liquefaction for hydrogen. Next slide, please. This is the picture of a different gaseous hydrogen used in Europe and US at the moment. And HTHP 300, which is Linde's design for the tube trailer, it can carry the hydrogen around 300 bar pressure, and that has a ability to payload of 950, versus there is a 500 bar hydrogen carrier, which is HTHP 500, which we are able to carry the hydrogen up to around 1130 payload kg, and that gives the additional hydrogen carrier into the one single ferry. But the cost we have to bear about is the additional compression cost of this hydrogen. Next slide, please. So based on this, Linde did some kind of the assessment that what's the right way of distributing the hydrogen when it is produced. And the result is that if you see here on the right hand side chart, it compares about the gaseous hydrogen at top, liquid hydrogen in middle, and the LOHC is the bottom, and then decide that what is the right way of distributing the hydrogen. Now, as I mentioned to you, it's also depend upon the end application, distance between the production site and the application site, as well as the demand of that hydrogen, the quantity of that hydrogen, decide what's the right medium of for transport. We also looked at ammonia and we also looked at methanol. So ammonia, LOHC, and methanol are more of a hydrogen carrier used for transporting the hydrogen from a inter-country transport, where it is a lower cost of the transport of the hydrogen from one country to other country, as well as the gaseous hydrogen and liquid hydrogen are more compared for the within the country transport. And what has been come out as a result is this. Can you go to the next slide? So just to give you quick comparison between the gaseous hydrogen, liquid hydrogen, and LOHC, we have looked at a number of customers in places where we have to provide the hydrogen distribution from the production. So let's say base case is a one customer. The next case is a 5 tons per day of hydrogen distribution, 20 customers, 50 tons per day of hydrogen with the 200 customers. The first chart is the gaseous hydrogen, middle chart is the liquid hydrogen, and the third is the hydrogen carrier as a LOHC. And this is been looked at for a 500-kilometer transport of hydrogen. If you see this, it's very clear that when you have a low distance, low capacity, then the gaseous hydrogen plays a most competitive mode of transport. If we have to transport a very high quantity, which is like a 50 tons per day or more, with a distance of more than 500 kilometers, the liquid hydrogen comes out to be the cheapest and most competitive solutions. LOHC, in either case within the same country transport, comes out to be the expensive solution compared to the pure form of hydrogen, because of its investment at the source as well as the discharge point for the deassociation of hydrogen. However, LOHC needs to be looked at and compared when there is an international transport from one place to the other place for the much longer distance. Okay, and this kind of gives the perspective that for the last mile delivery, what should be looked at when we decide to distribute the hydrogen. Next slide, please. The other thing also been very critical to look at is what's your end application. And the reason for this picture and this slide is if the end application is the mobility for the bus, trucks, and the cars, and then it is also very important that where is that location of hydrogen refueling stations and how it looks when you make the gaseous hydrogen based refueling stations as well as the liquid hydrogen based refueling stations. So if you see the left hand side, Linde has a both technology to compress this hydrogen for the 700 and 350 bar pressure to supply into the bus, trucks, heavy duties vehicles as well as the low passenger cars vehicles. With the cryogenic pump technology, we can use the liquid hydrogen and put into the nozzle of the cars. And we have a ionic compressor based solutions which can also use the gaseous hydrogen stored into the storage and put into the vehicles. Now if you see just the difference in the footprints and the design of the liquid hydrogen versus gaseous hydrogen refueling station, the left hand side will see the liquid hydrogen which is very elegant and very low footprint design. So liquid hydrogen, when you have a good high demand and when you are bringing the hydrogen far, it was also been looked at that the hydrogen carrying the liquid form is good. But at the same time, if it's within the congested city and when we need to do it between the major city, there's a refueling stations, liquid hydrogen also brings a very good advantage on the space versus if the demand is low and we will be putting somewhere the hydrogen refueling stations outskirt of the city and the demand is low or the operating window is low, we can also look at the gaseous hydrogen, but that requires a more footprint and higher storage area to put the hydrogen refueling stations. So in nutshell, if you see, the hydrogen delivery is very critical element to be considered when we transport the hydrogen from the production to the end applications. And all these aspects like the overall delivery cost, overall conditioning cost, overall compression cost, plus the footprint and the end application needs to be considered before we decide what's the right pathway to deliver this hydrogen. Okay, so thank you for this and very happy to take any questions you have.